Good morning, I'm Sangjin from Sungkyunkwan University in South Korea. I'm going to present a paper titled Reinforcement Learning Based SSD Cache Technique for Enhancing SSD Write Performance. Nowadays, creation and fresh memory is becoming a mainstream storage of SSD. It has a higher density and lower cost compared to TH flash memory. However, we can find that it has a slower performance and lower endurance than its previous generation memories. To hide the slow performance of cache memory, most recent cache-based SSDs adopt a hybrid SSD architecture. Hybrid SSD architecture has a partitioned SS region. The SS region is utilized as a cache space of the remaining cache region. By writing hot data at the SS region, the overall performance of hybrid SSD can be improved. There are two important factors to design a hybrid SSD. The first is the SS region size. To determine the size of the SS region, we should consider trade-off between capacity loss and SSD cache migration overhead. As shown in the picture, the capacity of an SS block is smaller than that of a cache block. Thus, the total capacity of SSD is listed as more fresh blocks are allocated to the SS region. On the contrary, a too small SS region will result in high migration costs, while increasing the write latency and write amplification factor. This is because data in the SS region must be migrated to the cache region when the pre-blocks in the SS region are insufficient. The second factor is the hardcode separation threshold. Considering the SS to cache migration cost, it is better to write only hot data at the SS region. Other cold data needs to be sent directly to the cache region. To distinguish between hot data and cold data, the hybrid SS can use the write request size. This is because small data tend to be frequently updated. In this slide, I'm going to review the existing SLC Cache Management Schemes. There are static scheme and dynamic scheme. The static scheme maintains a fixed SLC cache size and fixed hardcode separation threshold. The dynamic scheme adjusts the SLC cache size and hardcode separation threshold according to the system stage, which are like amount of storage data and workload patterns. Recently, several QHSS products began to adopt the dynamic scheme. They use a simple technique to adjust the SS cache size. For example, a proper SS region size for a given storage utilization is investigated at offline with representative workloads. Therefore, their performance can be degraded on the unexamined or variable workloads. To observe the problem of the current dynamic hybrid SSDs, we performed experiments with our trace-driven hybrid SSD simulator. Two real workloads were used, PC and YCSB-A. The PC trace includes a larger number of hot data compared to the YCSB-A database workloads. We examined the hybrid SSD performance with two different SSD cache setting policies. Setting 1 utilized the SSD cache more aggressively than setting 2. From the result, we can note that the better policy between setting 1 and setting 2 is different depending on the workloads and storage utilization. For example, in the PC workloads, when the initial storage is empty, setting 1 shows a better result than setting 2, since many write requests are serviced at the SS region without significant SSD to cache migration overhead. However, when the utilization is high, setting 1 shows a worse result due to high migration cost. Consequently, We need a more intelligent algorithm to adjust the SSD cache configuration, considering the dynamically changing system state. Without any prior knowledge about user workloads or storage characteristics, the reinforcement learning-based approach can learn how to find the optimal management policy. In the reinforcement learning, an agent learns to act optimally through observations and rewards from the environment. The purpose of reinforcement learning is to choose the action that maximizes cumulative rewards. We employ Q-learning. The agent calculates Q-values that tell the agent which action is right in a given state. The Q-running maintains a key data structure called Q-table to store Q-values. We also employ the E-grade algorithm for exploration that can maximize the total reward in the long time interval. Sometimes, the agent needs to select random action to find the optimal policy. This slide shows how the reinforcement learning can be applied to the dynamic SSD cache. At each time step, the environment defines the state based on the workload characteristic and the internal status of the SSD, and estimates the rewards for the previous action. The SSD Cache Manager, which is the agent, selects an action including changes of the SSD cache size and the hardcode separation thresholds. In the proposed scheme, each time step is defined as a predetermined cumulative amount of host write requests. To go into details about our scheme, algorithm 1 shows the pseudocode of the proposed SSD cache management. For the agent to run the optimal policy for the SSD cache management, we selected several features from host and the SSD subsystem to observe the change of environment. In this table, we used the SSD cache size, space utilization, and previous action for SSD states. SSD cache size and space utilization have strong influence on migration and garbage collection cost. The previous action includes the recent decision of the agent and the recent system state. We used demand for SSD write and update write frequency in SSD cache for host workload state. The first one represents how much hot data the host generates, and the second one means the intensity of hotness of the host data written in the SSD cache. The Q-table size is 5,186 bytes, which can be stored at an SSD flash page with a size of 16 kilobytes. It also can be cached in the internal DRAM of SSD. We need to consider all write costs to calculate the rewards of the previous action. SLC and QH write latency, migration, and garbage collection time have strong influence on write performance. Thus, we designed a reorder function by using these factors. Algorithm 2 shows the reorder function. After performing an action, we calculate recurrent cost and host write cost. And then we determine total write cost, which is a weighted sum of the host write cost and the recurrent cost. As the space utilization is higher, a higher weight is given to the recurrent cost and lower weight to the host write cost. This is because the impact of recurrent cost on the overall performance is more significant and higher space utilization. By giving a higher weight to the recurrent cost, the reduction on the SSD cache size can be accelerated when the space utilization is high. The final reward value is determined to be positive or negative, depending on the comparison region to the average total write cost. To evaluate the efficiency of the proposed method, we implemented a trace-driven hybrid SSD simulator. The simulator estimates the latency of each write by counting the number of SH or cache flash operations required to handle the request. Several flash memory and FTM parameters were computed as shown this slide. We compared the proposed RL-based technique with two previous dynamic SH cache techniques, utilizing aware self-tuning and dynamic write accelerator. The baseline method uses only cache blocks without SH cache. We use 6 workloads for simulating inputs collected with the block trace or Discman tool. We compared write throughput of different schemes with the 6 workloads. The results are normalized to that of the baseline method. The proposed method outperforms all other techniques under most workloads except for the case of YCSBA. Since most of the write requests are large and most of the data are held in YCSBA, the SSH cache was little utilized in the RL-based scheme. To analyze the behavior of SSH cache management techniques, we observed the number of allocated SSH blocks and the hardcode separation threshold at every 128 megabytes of host write. Compared to DWA and USD, the proposed technique adjusts more dynamically the SSH size and the hardcode separation threshold. In the PC workload, which has many frequently updated data, the proposed method allocates less number of SSH blocks than USD does, but maintains a large value of hardcode separation threshold to store as much hot data as possible in the SSH cache. This slide shows the breakdown of I/O execution time. The proposed methods reduce the cache to cache or SSH to SSH garbage collection overhead compared to USD. Note that USD performs the garbage collection within SSH blocks for host data, whereas our hybrid SSD does not have the SSH to SSH migration. The migration and garbage collection cost of the proposed technique are 65.2% lower than that of USD. Compared to DWA, the cache write overhead is reduced by the RL scheme. From the result, we can know that the proposed technique can find optimal SSH cache parameters on the various workloads. Since the RL-based technique reduces migration and garbage collection costs, the write amplification factor is also improved. The proposed scheme reduces the average write amplification factor by 20.3% over other techniques. In order to check the effect of the trained agent, we first trained an agent with several workloads of PIST, PON, YCSBA, and link matching. And then we observed the performance of the agent at other workloads of TPCC and OLTP. We compared the performance of pre-trained and untrained agent. The pre-trained agent improves write performance by up to 12.8% over the untrained agent. Therefore, we can know that the RL-based scheme can be applied quickly to a new system by using a pre-trained agent. Due to the increased bit density of flash memory, the hybrid SSD technology is becoming more and more important to enhance write performance. So we propose a RL-based SSH cache technique for the hybrid SSDs. The proposed method dynamically determines the optimal SSH cache parameters based on the system state. As a result, the write performance is significantly enhanced without any prior knowledge about host workload or storage characteristics. As future work, we have a plan to examine the effect of the proposed RL scheme at a real SSD subsystem. Another work is to apply the technique at multi-stream SSDs. We can utilize the stream information to determine the optimal number of SSD blocks of each stream by observing the data lifetime of the stream. Thank you for listening.